Hi, I'm Fishing Paul and welcome to the final part of lesson 2 of my QMD tutorial series. In the previous two parts, we saw what are particles and how they work. We saw what is a linear accelerator, how does it work and how is it built. We designed a linear accelerator in order to accelerate a beam of boron ions to the desired energy and focus values. And in this lesson, we will use this very same beam to produce p-type doped silicon via a target chamber. We will also show a couple additional particle chambers, which can be used to reuse or recycle beams. We'll start the lesson with the target chamber. The target chamber is a particle chamber multiblock where particle beams collide with an item or fluid target, converting it into a different item or fluid and possibly emitting more particle beams in the process. Target chamber recipes, as we've seen, consist of the input beam, the input item or fluid, aka target, the output item or fluid, and between 0 to 3 output beams. Each recipe has 5 stats: an amount, the energy range, a minimum focus, the cross-section, and a released energy. We have seen the amount, the energy, and the minimum focus, but we have ignored so far the cross-section and the released energy stats because they weren't particularly relevant to our target chamber recipe. So, what is cross-section? The cross-section shows how many particles perform a successful nuclear reaction. Lower cross-section means a higher amount of particles needed, and lower PU per tick on the produced output beams. Recipes generally require 1 million PU divided by the cross-section to perform. For example, the recipe we want to do has a cross-section of 100%, and thus the amount is 1 million PU. But if we take this first recipe here, you see it has a cross-section of 20%, and the amount required is, of course, 5 times higher. Then we've got the released energy. The released energy is how much energy is gained or lost during the nuclear reaction. The beam input energy plus the released energy is split equally amongst the PU, not the number of beams, of the output beams. So, when we do a recipe in a target chamber, extra particle beams may be emitted. What are those beams' stats? Start from the amount. The amount that we see written here basically tells us how many PU of this particle will be released for every 1 PU of input. This amount is then multiplied by the cross-section and the chamber's efficiency. Assuming a 10 kPu per tick beam and a chamber efficiency of 100%, we would have 3 times 10,000 times 20% times 100%. And all that resolves to 6 kPu per tick. Now let's go to the energy. The energy will be equal to the input energy plus the released energy, and all that divided by the total amount. So let's say we have a 400 kilo-electron-volt input, which means the total energy available is 9.08 mega-electron-volt. We have 3 particles on the output, so the particles will get 9.08 divided by 3 equals 3.027 mega-electron-volt. Let's assume that in this middle output here we have a 2 PU neutron beam. Then the energy would be split into 5. So both of these beams would have 9.08 divided by 5, 1.816 mega-electron-volt of energy. And now let's go to the focus. The focus is a little bit more complicated, mainly because the particle changes midway. Let's demonstrate what I mean. Let's do this very simplified target chamber here. our input beam comes in from the blue input on the left. It collides in the particle chamber with some item, and then this collision produces a smaller particle which gets released in the red output on the right. The way to calculate focus is this. We take the input focus, and then we will make the assumption that the nuclear reaction happens in the middle of the particle chamber block, which means that our input beam will travel the total length of our target chamber divided by 2. And the other half of this path will be traveled by the output beam. So the focus lost is how much focus the input beam loses and how much focus the output beam loses. The input beam will lose, of course, its own focus loss per block times the length divided by 2, and then the output beam is going to lose focus equal to its own focus loss per block times the length divided by 2. In our case, we have a 10 kPa per tick input of protons with a charge of +1, and those turn into 6 kPa per tick of alpha particles with a charge of 2. Let's calculate the focus losses of each particle. The 10 kPa per tick proton beam has a focus loss of 0.04 per block, and the 6 kPa per tick alpha particle beam has a focus loss of 0.051 focus per block. Now, let's see how much focus we expect to get at the exit. Let's suppose that the proton beam enters with a focus of 1, so the focus loss is equal to 0.04 times 5 divided by 2 plus 0.051 times 5 divided by 2. The total focus loss is 0.2275 focus, which means that the alpha particle beam will have a focus at the exit equal to 0.7725. It's complicated, but once you get it, it's kind of simple. Let's talk about detectors. Detectors are special blocks which let you increase your particle chamber's efficiency at the cost of some power. Every detector has 3 stats. It has a particle efficiency stat, which is how much efficiency it adds. It has a base power stat, which is how much power it costs to operate, and it has a distance stat. All detectors, in order to provide their efficiency, must be within a certain distance of the particle chamber. The distance is calculated as taxi cab distance. To simplify it, count how many blocks it takes you to get from the particle chamber to the detector, but only count via adjacent blocks. Do not count any diagonal blocks. All detectors can contribute up until the point where the target chamber efficiency times the cross-section of the recipe reaches 100%. Beyond that point, they do not contribute any further to efficiency and therefore only waste power. We had a brief chat about the target chamber mechanics. Let's go into building it. A target chamber is a hollow cube with a side of 3, 5, 7 or 9 blocks made out of particle chamber casings. I will build a 5 by 5 by 5 chamber to demonstrate. Here is the frame. I'm going to turn on the printer. And this is the empty casing. Now we will place a beam port, let's say on this side. It doesn't really matter. And then from this beam port, we're going to place particle chamber beam blocks, the equivalent of accelerator beam blocks for particle chambers, until we reach the middle of the multi-block. It just takes one block, and there in the middle we will place a particle chamber. Now, depending on the amount of output beams you will have from the recipe you want to do, you will need to make the appropriate amount of output beam lines. For the sake of example and completeness, I will place down all 3 possible beam lines, but you don't need to. So to place the beamlines, we pretty much do the reverse thing. We start from the particle chamber and then extend outwards using beam blocks until we hit the casing. And where the casing meets our beams, we place a beam port, turn it into output mode, and there we go. So now, each one of these beam ports, what beam does it correspond to? Let's look up down on the accelerator, and let's assume that the input port is west. The north port corresponds to the top output, the east port to the middle output, and the south port to the bottom output. I'm going to overlay on screen an empty target chamber recipe so that you can visualize what I mean. Okay. And now we can place detectors in the middle if we want, but the recipe we will do does not have any reason to place detectors because its cross-section is already 100%. So to close it off, we will build some glass here to form the ceiling. Then we'll need to place 2 item ports for automation, an energy port to feed it power, and a target chamber controller to form the multiblock. Another multiblock is pretty much ready to go. We just need to give it power and a particle source. All particle names will be in the wiki if you want to look them up. So I'm going to make a 1 kPu per tick proton beam because why not? Give it 500 kilo electron volt of energy and 0.2 focus. And as you can see, the chamber is on. This is a big difference to accelerators, which do require a redstone signal to turn on. The chambers turn on automatically. And so we have our proton here, and it's ready to do recipes if we have the proper target. So, let's say we have output beams. What do we do with them? For example, let's place boron 11 to perform the recipe we have, and we get alpha particles out. What can we do with those alpha particles? All output beams pretty much have 3 uses. Use 1 is we can reuse them in another recipe. If the energy, the particle, and the focus is right, then we could just use them in another recipe. And even if they aren't right, we could use an accelerator to bring them up to speed. The other use we can do is the decay chamber. The decay chamber allows us to decay particles into other particles. We just input a beam, and this beam gets converted into 1 to 3 other beams. The same rules apply in terms of the amount, the energy, and the focus of each beam, just like in target chamber. We just have to remove the item and fluid ports from target chamber and replace the target chamber controller with the decay chamber controller. And otherwise, the multiblock is pretty much identical. As you can see, it works just fine. And now you will ask, why would I want to use a decay chamber? That's a very good question. Some particles, like neutrons, can't be manipulated further, as in can't be accelerated or bent, because they have no charge. But if we use a decay chamber, we can turn them into other particles. Specifically, a neutron can turn into protons, electrons, and electron antineutrinos. So we have protons here and electrons here. Electrons and protons carry a charge and therefore can't be manipulated further. In short, we can use decay chambers to turn particles we can't do anything with into other particles which we can do things with. And the final use of an output beam is to recycle it via a beam dump. The beam dump receives a particle beam, and it can turn it into a liquid. For example, it can collect protons to make hydrogen. To build a beam dump, it's pretty simple. I will put down a schematic. We need to do the following. We need to place a particle chamber right in the middle, and then surround this particle chamber with a 3x3x3 cube of particle chamber casings. Then we need to replace some casings with a beam dump controller, an energy port, a beam input port, and a fluid output port. Let's print it. And then we're going to use the multitool to set this into output, and it's formed. I will also connect this beam port, so this beam pipe, so that we can convert protons into hydrogen. And as you can see, it's working. We just need to feed some power, and we're getting hydrogen. So that's what we can do with a beam dump. And now let's go back to our accelerator. In order to produce the p-type doped silicon that we've been wanting so bad since the beginning of the lesson. So to do that, we'll bring up this schematic. Now, as the p-type doped silicon recipe has a cross-section of 100%, we don't need to use any extra detectors. Therefore, we can simply make a 3x3x3 target chamber. Also, we can just make the target chamber touch directly the output of our accelerator, because beams ports can automatically output to adjacent blocks. You do not need to put a beamline pipe between the multi-blocks, unless of course they're the same type. We can put accelerator to accelerator, and we can put a target chamber to target chamber. It's exactly what I demonstrated over here. So let's place the target chamber. Let's print it. The target chamber is formed and it's working. We have boron ions here coming in. We feed it power. We will place servos to extract the silicon, and as you can see, we get p-type doped silicon. And that concludes the part and this lesson. Let's go to the lesson recap. So we have reached the end of lesson 2. Let's do a whole lesson recap. We started by looking at how particles are defined and how they work. Then we looked at how a linear accelerator works and how it is built. We then combined a particle and a linear accelerator to make a particle beam with the desired energy and focus properties. And then this particle beam, we put it into a target chamber to create new items. We also demonstrated that we could put particle beams through a decay chamber to create new particles. And we also demonstrated that you can recycle beams back into fluids using the beam dump. And now we have p-type doped silicon. What's next? With p-type doped silicon, we can create advanced circuits, which gives us access to advanced accelerator multiblocks. These multiblocks can help us either achieve much greater energies at a higher energy cost and space cost, but we also get access to multiblocks that can help us literally bend beams to our will. So that's what you have to look forward for in the next lesson. So I bid you farewell. I will see you in the next video. Goodbye.